Hi, I'm Dr. Rod Hebden, and welcome to this episode of Sculpting Tomorrow, where we try and get behind all the media hype, whether it's overinflating the excitement of something that's going on or scaremongering about it, and actually speak to real people who are at the cutting edge, doing the real research, helping shape our future. So today we've got a not quite doctor again, Matt Brenton from Loughborough University. So third year PhD student, is that right?
Yeah, so I'm in my third year of my PhD now. I've been working on these low-cost hydrogen projects for 3 years.
Right, and so how did you get involved? I mean, were you always into science as a kid, or is that something that came out new? I mean, presumably as a kid you weren't particularly into hydrogen.
No, so the hydrogen is definitely a new part of my interests. I've always been interested in science. I did a chemical engineering degree at university, did a master's in renewable energy because that's where my interests really lie.
Right.
As part of that, I did a low-cost hydrogen thesis on this concept called the lead-acid battery electrolyser. And then basically that span into what is now my PhD project.
Okay, because I mean, we'll get onto this later, but you're doing projects which are hydrogen. People think of as, hydrogen cars, maybe we'll touch on that. But you're doing stuff like in Africa and all sorts of other ways of using it, kind of in other situations. But I mean, so when you're a kid though, was it your dad worked in science engineering, or your mum?
Yeah, so my dad worked as an engineer, I think primarily mechanical. So he definitely passed down a lot of that scientific interest and engineering interest.
Okay.
And some of his practical skills as well.
Okay, so you did have you did have an upbringing. So that makes sense where that came from. So getting into the area we're looking at, your research group, is that all hydrogen at Loughborough?
So the team that I'm a part of is very much focused on this one technology, the battery electrolyser. So there's about 6 of us working on the project at the moment. But my department, the Centre for Renewable Energy Systems Technology, covers solar power, different forms of energy storage like thermal.
But your area has been entirely on hydrogen. So tell me about that, or just what does it mean? So we talk about hydrogen power a lot, and then there's get into all sorts of debates about the pros and cons. What basically is it? How does it work?
So what I'm working on specifically is battery electrolysers. So an electrolyser is a way of splitting water into hydrogen and oxygen in order to then collect that hydrogen and use it as an alternative fuel. So some industries like steel and cement making, they rely on a lot of fossil fuels to heat things up. Hydrogen can be used as a substitute for some of those, and therefore reduce the carbon emissions of those industries. So,
and you're working on so once you've got the hydrogen, and then that's going to get used in fuel cells or burnt, I guess.
Yeah.
So hydrogen gets used in lots of different places, but you're working on how you produce the hydrogen. Because are there other ways?
Yeah, so at the moment, the primary way of producing hydrogen is something called steam methane reformation. And that's basically a very carbon intensive process. It involves heating up methane with steam. And in the process, it releases a lot of carbon dioxide. Also, to reach the high heats required, uses a lot of fossil fuels. So that is a very bad way of making hydrogen. So we're looking to try and replace that.
Is that what they call blue hydrogen?
So that's grey hydrogen.
Okay.
Blue hydrogen is the same process, but you introduce carbon capture.
Okay.
In the UK, blue hydrogen is steam methane reformation with a 95% carbon capture rate.
Okay.
But that's still not perfect. Whereas green hydrogen, which is what we're looking at, instead you're doing this electrolysis process of water and you're powering it purely with renewable energy. So you've got no emissions associated with the production of the energy to form it, and you've got none associated with the actual creating of the hydrogen from the water either.
Okay, so that feels like that's kind of like the holy grail from a hydrogen perspective, because I think it kind of became really big a few years ago, and then quickly people started going, where are you getting the hydrogen from? Well, we're using electricity, and where did the electricity come from, or using the methane reformation, and I think I even read articles showing that the carbon emissions of some hydrogen productions were worse than just burning the oil in the first place, and certainly not significantly better. But you're doing it without essentially with minimal carbon emissions from the very beginning, if you're using renewables to create electricity and then doing hydrolysis. So what is the reason why we don't just do this anyway, if we already can do it? why are we even bothering with other ways of producing hydrogen?
So at the moment, hydrogen is not just used for things like transport or cement making. It's used as a process gas in industry. So fertilizers are made from hydrogen combined with nitrogen to make ammonia compounds. And there's some other processes as well that require hydrogen feedstock. So that's why we're currently producing it using these old methods that are very carbon intensive. Now that we're looking at these new industries with a hydrogen focus, we need new methods of generation. So that's the electrolysis. That's what I'm working on.
So, I mean, why is it so difficult? Why is electrolysis such a problem that we still, is it more expensive to produce electricity that way? And you're working on electrolysis, so you're trying to make the process better. What are the problems?
Mm-hmm. So historically, our electricity grids are primarily powered by fossil fuel emitting sources, coal, natural gas. As we're increasingly bringing online renewable energy, it's not necessarily always generating when we're demanding from the grid. Yeah. So we need a way of storing that energy, and that can be hydrogen. So that could be for your seasonal energy demand, because we get in the UK, for example, there's a huge seasonal variation between what we want versus what we're generating. So in the summer, we've got quite a lot of PV now, so we generate quite a lot. In the winter, it's cold, it's dark, you want your lights on, you're not generating much PV. It's a problem area. So now that we've brought those renewables online, we're looking for a new energy vector to be able to take that excess energy in the summer and put it somewhere so that we can access it in the winter months.
Kind of smoothing it off, because
exactly.
When it's really windy and really sunny, we've got more energy than we know what to do with. Yeah. And when the wind drops and it's cloudy, we're kind of stuffed at the moment. So it's kind of storing the excess to use it in the gap.
Yeah, exactly.
I think we on a previous podcast had a bit of rock here, which I didn't explain, and the rock was from the inside of a mountain in North Wales, which was a very similar idea. It was so energy storage. Mm-hmm. So when at normal times they would pump the water up from the lake at the bottom to the lake at the top, and when everyone turned their kettles on in Coronation Street, when the adverts came on, they'd let the water out, and it would produce electricity through a turbine. So it's kind of essentially like about peak demand and storage, essentially what you're doing, but using hydrogen rather than a lake. To store the energy.
So those water-based systems are great, and the fact that they're fairly easy to implement in areas where you can implement them makes them a really good storage option. But you're limited in scope for locations, so we need the new hydrogen or batteries for these.
You can't put a mountain in a lake everywhere.
No, exactly.
Basically, if you could do that, well, be good for tourism as well.
And we're doing it all the time,
Yeah, quite. So we sort of talk about your PhD, your actual bit of research then. Mm-hmm. So what is your area in terms of making electrolysis better? What's the angle?
So at the moment, as you mentioned before, electrolysis is very expensive, and that's in part due to the cost of renewable electricity, right? Because most of it's just being used by general consumers. The other side is that you have a very high upfront cost to some of these electrolyzers. So some of them are using things like platinum and iridium, which are rare earth metals. They're expensive. They've got high embodied carbon, which is the amount of CO2 associated with extracting them from the earth. So the idea was to look at something that used lower cost materials, more earth abundant materials. And so that's taken the form of this lead acid battery electrolyzer, which is principally repurposing a lead acid battery technology for use as an electrolyzer as well.
Okay.
This actually means that you've got two revenue streams from the same energy, because not only can you generate hydrogen from it, as I said, when it's fully charged, but you can be charging and discharging it as a battery, so you can use it for some of the grid applications that they're using battery systems for, starting to use battery systems for now.
Okay. So what have you got to show? So you brought in a couple of props. Is that one of the things you're working on?
Yeah, so this is what my team have been working on. And it's
is this the side you can't show anyone?
That's in the middle.
Oh, okay.
So this is a prototype lead acid battery electrolyzer, but we've got 3D printed parts for some of it. We're starting to look towards proper production for some of these, so injection molding the lid.
So for people who are listening to the audio version, essentially what you've got out looks like one of the big Tupperware containers for cereal. So it's essentially a big rectangular, see-through sort of transparent tub with a lid on it. But whereas it would normally be full of cornflakes, I don't know what's inside it. To me, it looks like a kind of sheet of solar panel. It's kind of a sort of big black rectangles inside there, and then a bunch of kind of ports and knobs and bits and pieces on the top. So what exactly are we looking at?
Yeah, so the two big plates that you were talking about are the lead acid plates, such that you would find in a standard lead acid battery. Okay. So quite similar to the ones that you find in the starter battery for your car.
And this is like you do in even GCSE chemistry, isn't it? Where you always had to kind of draw a diagram of you label your cathode and your anode,
yeah,
and bubbling going on and all that sort of stuff, and trying to remember which way is around a cathode and an ion and all that sort of stuff. And I've had to teach my kid this, and it's really confusing.
Yeah,
but essentially it's the same technology. It's the basics of it.
Fundamentally, yes. It's just like sticking your copper and zinc into a beaker, but right. We've had to change it a little bit because we want to capture the gases that we're releasing.
Okay.
Which is why we've developed this lid. Underneath the lid, there's a separator. So ordinarily in a battery, you'd have lots of plate pairs stacked up against each other.
Okay.
But if you're using that for gassing, all the gases are mixing, which if you're mixing hydrogen and oxygen, is a little bit dangerous because then you have a very combustible explosive mixture forming.
That sounds a little bit dangerous.
So we're trying to avoid that with ours by introducing this separation, and in the top there's two different chambers, and that's where the gas enters before leaving through these terminals on the top. So your hydrogen comes out of here and oxygen here. I'm sorry,
how does the hydrogen and oxygen know which? How do you separate those? Because it's just gases bubbling off.
So each gas only appears at its own electrode.
Okay.
So oxygen always forms at the positive electrode, and hydrogen always forms at the negative.
Okay.
And that's just not true of the battery electrolyzer, that's all electrolyzers, which is how they normally achieve separation in those as well, is to basically do the separation at the point of generation because it's more expensive afterwards.
Yeah, okay.
Most of the time.
So they're just naturally bubbling at different points, and you're just letting it bubble away, and it just floats to the top, and you capture it.
Yeah.
Okay.
So at the moment, a lot of those electrolyzers use quite expensive separation technology. One of the innovations that we can't see in here is our...
Can I peek?
maybe afterwards. Is a novel way of separating the gases that we hope will have good longevity and reduce the cost of this.
Okay.
So on the top, there are two holes for terminals, and that's where you make your electrical connection. So that's to pass your current in and out of the cell for both charging, discharging, and also for the electrolysis. And then as you're electrolyzing water, you're losing water from the system, so you need to top up, which is just the purpose of this other connection on here.
So is it, when people talk about hydrogen, immediately the first question say is danger. We have these ideas hydrogen being really dangerous and flammable, and then if you're old enough, you imagine, the giant sort of blimps blowing up, all this sort of stuff. And then you've already mentioned the potential for it being dangerous. So is it dangerous? Should we be doing this at all? Should this be in the podcast studio?
So I think we're safe here.
Because Chris is starting to edge towards the door.
Yes, we should, as with natural gas in our homes, we need to be concerned about the safety standards.
Okay.
But rest assured, there are UK standards in place to make sure that we're not going to have explosive mixtures just forming in our homes if we're getting it pumped into our homes for central heating, for example. So natural gas is similar to hydrogen, is odorless and transparent. So if you had a leak in your home, you don't know that it's happening. That's why they add a scent to it so that we can detect it in our own homes as people. And
so when you smell gas at home, you're not really smelling gas, you're smelling what they added.
Yeah, exactly. Okay. So potentially if we're implementing hydrogen for UK homes, then we'll be adding similar scents. There's already testing going on for that. There's lots of research happening in that field to try and find something safe and affordable to keep these systems safe.
Okay. But in your other applications, because that's not necessarily domestic or this, but the actual thing itself, not too worried about. I think we've also got now people worried about shared on social media for various reasons are pictures of Teslas exploding, lots of stuff or setting on fire, and then essentially if you it's a funny thing, we've got ourselves into a mess with electric scooters, haven't we? Where they're not legal, and so people are just importing them, and the quality's not always good, and those are exploding all over the place as well. I mean, is this something we should be worried about as a we're introducing another explosion risk into our energy system?
So in terms of this cell itself, lead acid batteries don't possess that same quality as lithium of exploding sometimes. It's a much safer and more inert battery chemistry in that regard. In terms of the hydrogen itself, so for example in automation, in automotive, such that you mentioned
in cars,
in cars, if you pierce the tank of a hydrogen tank, then yes, you will be forming sort of a potentially explosive gas mixture, but hydrogen is 14 times more buoyant than air, so it tends to disperse really quickly, and actually the area around which an explosion might form is quite small.
Okay. So you say more buoyant. Basically, hydrogen's really light.
Yeah.
So whereas if you pierce a petrol tank, you'll have the pool of petrol, which can blow up right where you're standing. Hydrogen just disappears into the air and it's gone.
Yeah, exactly.
So it's really hard to get an explosion from hydrogen, actually. Okay, that's reassuring. And so the differences with yours in terms of that, the innovation is essentially about the gas capturing.
Yeah, so fundamentally it's not very different to your normal lead acid battery. The plates are the same, so we're actually, if you look on this, this case is provided by our partners at Hoppecker. Right. So are the plates. The innovations come from the lid, and the gas separation, like you say, and also the fact that in a conventional lead acid battery, you're trying as hard as you possibly can to not gas, because that's causing you problems. Sometimes it's forming explosive mixtures inside the cells, which can cause problems, as you might expect if they explode. Also, because we're deliberately doing it, we can be sort of catalysing the processes and making improvements around increasing the gassing, whereas the industry's always looked towards minimising that gassing over time.
Okay. Because you've also brought in something else which kind of looks kind of cool on the table. But
yeah, so it's something that we might use the hydrogen for that we've generated inside that inside the battery electrolyzer.
What is this?
So this is a little fuel cell car that we've prepared earlier.
Nice.
And
it's kind of hamster-sized. So again, listening audio, I mean, it does look kind of like something from Futurama, really. It's kind of a tiny little futuristic-looking car made of plastic. It's kind of a toy thing, but with two little little cups of water at the back.
Yeah. And each of those cups of water contains, one contains hydrogen, the other one contains oxygen.
Each of these,
there's upturned domes inside, and those are containing the gases.
So there's liquid on the top, which is just water.
Yeah.
Is that? And then upturned domes, and there's gases in each of those. I hadn't spotted those. Okay. So what is this? This is not how a hydrogen car is going to work in expanded, is it?
Fundamentally, yes.
Okay. So talk me through this.
So what we have here is a hydrogen-powered car, and we have at the back our hydrogen storage. So in here we've got hydrogen, and in the other one we've got oxygen. These are being fed into this central unit, which is probably some sort of platinum group metal.
It looks a bit like the battery you just had out, but miniature. Are these is it analogous? So as you had your lead catalyzer thing, this is a similar, or is this something completely different?
It's something completely, so the materials are different, and we're effectively doing the opposite process.
Right.
So in there we were generating hydrogen and oxygen. Yeah. In here we're going to be recombining it. Okay. And in the process that releases electrons, drives an electrical current, and gives us electricity. And so that's how we might power EVs, but with hydrogen instead of batteries.
So you don't have to charge the thing for ages. You put in hydrogen, and that creates your electricity.
Yeah, exactly. So it'd be more similar to current ways of filling up your car, going to a garage and topping up, not having to wait an hour or queue with other EV drivers. So I'll just turn it on. Hopefully it will run.
So it's now going to drive off the edge.
It's working
explode.
too well, if anything.
So this is literally generating. This is an actual functioning. It's going in reverse now. There we go. As soon as I move it forward, it just drives forward. So this is a functioning hydrogen car.
Yeah, exactly.
Actually using hydrogen drives, and this is exactly as we would have potentially to drive. And are there any of these that actually exist, full-size hydrogen cars? Or is it just toys and in theory?
So there's a couple of hydrogen cars on the market. One of them is the Toyota Mirai.
Okay.
BMW are also bringing out hydrogen cars soon. So this is something that is viable. It is something that's on the market. It's just that there's not currently the infrastructure in place for wider uptake for ordinary people. So there's not really any hydrogen fueling stations anywhere.
Yeah.
So from here you'd have to venture out to London if you wanted to fill up, or there's a few up in Scotland.
So it's an infrastructure thing. So, weirdly, Swindon used to have 2 or 3 hydrogen fueling stations, but they were kind of demonstration, and there was no. It's that chicken and egg thing of put a bit of infrastructure in, and then they never got used because there were not enough need for. There were no hydrogen vehicles, and so they didn't work. And then it just kind of a cycle because you need kind of it's infrastructure versus vehicles. Is that the main thing stopping hydrogen cars? Do you think hydrogen is realistically what cars are realistically what hydrogen is going to be used for? And do you think it's the main use, or is it?
So I certainly don't think it's the primary use for hydrogen. So as I said before, currently most hydrogen in the world, I think it's over 90% is used for processed gases for things. So that's the first place that green hydrogen needs to be deployed. We also need to be using it in cement and steel works where they need a lot of heat for these industries.
Right.
Freight and sort of not personal transportation, so cargo ships, lorries, maybe trains, depending on the situation. So again, one of your problems with using it in a fuel cell is that you're using these platinum group metals. Okay. And that will be a constrained resource. If everyone has their own fuel cell in their car, then there might not be quite enough for everyone to go around. So
in theory, there's no reason why we can't use hydrogen fuel cells in cars, but actually that's not where the story ends for hydrogen at all. It's just kind of one possible use.
Of many applications.
Weirdly, Swindon has, you might not know this, maybe you do, the first ever hydrogen car in the world.
Oh, really?
There you go, see? Yeah. So just across the motorway, up at the Science Museum. The Science Museum owns a big storage site, big former airfield. And in there is the very first hydrogen car in the world. Well, not a production car. So the brand you might have even heard of, it was a DAF. And it was created, your dad might know about it. It was actually put together by people up in Solihull. So they were just looking for new things to do with the fuel cell car, with a fuel cell, and thought, could we put it in a car? And so I think it's a Shell fuel cell, and they put it in this DAF vehicle just as a demonstration thing. So that was, I think that was back in the 60s.
Wow.
They kind of, the idea is there and it seems to work, but it's not necessarily where it's going to be actually implemented for the most part.
Yeah, and the other alternative is that you can burn hydrogen in an internal combustion engine. So there are supposedly some studies showing that you can run it without making too many modifications to existing engines, or it could be a case of designing new ones from the ground up so that you're burning hydrogen in them rather than using them in a fuel cell like this one is.
Okay. And what other what other uses are there? What other applications or use cases?
So the big ones are long distance travel, so freight, maybe aerospace is a possible application. These really hard to decarbonise industries, heavy industries that require a lot of heat. Cooking as well, so maybe you could get gas pumped into your home instead of natural gas as we do at the moment. Or for space heating as well. Those are some of the main sort of hard to decarbonise sectors that if we swap them all to electricity, we might be overstraining the grid if we're charging batteries all the time.
Yeah, okay. And there's something, the project that I think you're working on in Africa. What was that all about?
Mm-hmm. So the project that I'm very lucky to be a part of is called Low Cell H2. And Low Cell H2 is aimed at providing clean, affordable energy to remote communities in Africa. Currently, we're looking to deploy 2 pilots to the Ivory Coast and Zambia. And the idea is that these communities, they're not currently connected to any sort of national grid.
Okay.
They might have poor or no energy access from an electricity standpoint. So it's deploying solar panels and batteries to individual households and setting them up in a new microgrid. That way the households will be able to support one another in terms of overall energy.
So it's sort of community scale.
Yeah,
really?
so about 20 or 30 households is that's the scope of the project. And what we're doing as part of that is deploying a battery electrolyser to the same site, and that will provide hydrogen for clean cooking. Or if they have an alternative use for it, then they could set up some sort of small industry using the hydrogen.
So the benefit to them really is that the other alternatives are a problem. So you don't have grid access. So it's not you can get electricity from anywhere else. Yeah. So actually, because you're generating your own hydrogen, and then you can use that for other things, it's kind of self-contained. Is that the purpose of it? Just kind of it's a whole holistic sort of circular thing going on.
Yeah. So it is that, and it is helping to give people that energy access that enables sort of better education, enables work into the evening, and new industries that sort of don't exist in these places already. So, as I mentioned, they could use it for cooking. At the moment, across Africa, 2 in 3 children are exposed to high levels of indoor air pollution, and a lot of that is because they're using solid fuels. So that's charcoal, wood, and other forms of biomass. And the problem with those is they release lots of particulate emissions and carbon monoxide emissions, and that's really damaging for respiratory health.
But essentially the main issue is you're burning stuff in your house and then breathing in the particulates.
Yeah.
So you're providing essentially clean energy from a carbon perspective, but also respiratory health.
Yeah.
And we've been through a weird thing in this country, haven't we, where we kind of pushed everyone to go from petrol to diesel because it was lower carbon emissions, only to discover the particulates from diesel weren't particularly great either. Now we're banning those in cities and moving away. So it's kind of there's always kind of implications you're not always expecting in these things. But whereas what you're doing is essentially killing both 2 birds, 1 stone, aren't you? So do you think that's a project that will be useful intellectually, like it's kind of, that's an interesting challenge and that'll work and it'll teach us things, or do you think that's a realistic thing for communities, remote communities to use? Do you think that's scalable?
Well, of course, the hope is that it is scalable, and that we will be able to help more people, because the idea of it and the ability to give this access to energy, this ability to help people out of energy poverty is really critical. So there's a UN directive that's aimed at helping, that's goal is to give everyone access to clean, affordable energy. So if that could be a part of that solution, that would be a really brilliant thing. In terms of whether I think it will be, it's a case of getting it out there and actually testing it and seeing how it works, how the community interact with one another, and getting a better understanding of how this actually functions in the real world. It's one thing for us to test it in the labs, it's another thing for it to actually be deployed.
Yeah, well, it feels like, what do you always worry with these things is, we're testing this and we think it might be interesting, but then you put it in this community, it doesn't work, and then you go away again leaving all this mess or kind of unfulfilled promises. But it sounds like it's a real viable thing that hopefully will have legacy. So how long has that been going?
So the project started in January of last year.
Okay.
And it's in collaboration with sort of 10 other companies and institutions from around the world. So the people who are providing the solar panels and battery side, for example, that sort of energy management system are from Pakistan. We've got people doing the holistic management from France and Tunisia. So it's very multidisciplinary, very interesting project to be a part of.
Yeah, and so massive collaboration between universities, I guess there's probably government involved, there must be funding from UKRI and that sort of thing.
Yes,
but actually companies getting involved too. So I mean, it sounds fascinating. And is that on the Loughborough website as well?
So LOCEL has its own website, which is locelh2.org.
Okay, I'll check that out. So what do you think, what are you going to do when you finish your PhD? Do you know what the future holds for you? How's your PhD going? I mean, they're meant to be 3 years, mine took 4, but
I think it's the question that everybody dreads, isn't it? How's the PhD going? It's going okay. I've got a lot of data to work with, so we've been doing these durability tests on the cells ahead of the deployment, so we need to make sure that what we're giving doesn't fail out there, or at least to the best of our knowledge won't fail out there. So I've got a lot of data to work with. I am trying to write up at the moment amongst all the chaos, but you know, building the system is quite sort of all-consuming at the minute. And I'm also trying to work on a side project almost of another chemistry. So we're focusing on lead acid in that consortium, but I'm working with some people at the University of Calgary to try and develop vanadium battery electrolyzer technology as well.
What's the benefit of vanadium other than sounding cool?
So mostly it's sounding cool.
It's a bit Marvel. It's not far off vibranium.
So vanadium flow cells are different to your conventional battery, where the energy is stored in the plate. So the total energy that you can store is dependent on the size of your electrodes, basically. In a vanadium flow cell, instead, it's stored in the electrolyte. So you can, instead of it just having to be held in the single cell, you can have a separate tank that's full of vanadium, and that's all charged. And slowly you can either charge or discharge that to store much more energy, in theory, for sort of a lower cost. And that's more for national grid storage applications.
Okay, just the scale of the thing.
Yeah.
Whereas you couldn't scale up these batteries in that way quite so easily.
Well, so there are examples of really large battery balancing plants already in the world. I can't remember what the figure is for the size of the largest lead acid battery one, but they are out there. Like, it is proving scalable in that.
Numbers are only, they're impressive. We don't know what they mean anyway, but very big ones.
A huge number.
A huge number, really impressive number. But you think, so the vanadium ones are kind of essentially another way of doing that and getting the scale.
Yeah, potentially. So that testing, you know, you've just seen the cell there, and it's sort of 50 centimeters tall. We're testing with a 5 centimeter square electrode area there, so that's much more early days, and electrode durability for that will be an issue for sure.
Okay, so here's some questions no preparation for at all. But what do you think on the big ticket? If we could solve that, it would make a huge difference, either in terms of the tech or an application where you think, wow, if we could get it right, hydrogen would be brilliant for that.
That is a good question that you didn't ask me.
No preparation at all.
Beforehand.
It's kind of what do you think? What do you think the future is? You know, you kind of know what you're working on now, but actually, what do you see as being potentially interesting future for it?
So I think reducing our use of these constrained resources. So things like platinum and iridium, there are technologies emerging, or there are options where you reduce the amount that you need in a single cell, so in a single unit. So if you can bring that down, then in theory there'll be more of it to go round, and therefore we can be looking to phase out more fossil fuels in more countries, and it won't just be a case of industrialised nations sort of hogging all the green points.
Okay, because short supply of the materials, and we can afford them, and we leave them without, but we might mine them from their countries.
Yeah, exactly.
A little bit of that, because mining becomes a big issue, doesn't it, for kind of battery technology sometimes. Okay.
It certainly does. I mean, most of the cobalt comes out of the DRC, and it's another one where, 20 years ago no one would have predicted that cobalt would be a constrained resource, and now all of a sudden it's crazy.
Yeah. Okay. Because I mean it's a really key thing, because we have this. Kate Raworth, if you don't know her, look her up. Brilliant economist, and talks about the donut economics. So essentially, we're trying to avoid breaching our environmental constraints on the outside, whilst also trying to avoid stamping on a human resources on the inside. So we could make brilliant electric cars, which reduces carbon emissions, but if it means mining the hell out of countries and affecting local populations, that so we have to somehow manage to find that kind of sweet bit between those two types of constraints. So I guess this kind of technology where you're kind of actually what are the other materials we can use, or can we use them more efficiently, is kind of addressing that. Because I do think we feel like in the media we often get this kind of, people like to have a go at electric cars and say, but what about the mining? That means they're terrible. And actually it doesn't mean that. It means we've got other things we need to work on to kind of improve the technology. It's not the researchers not aware of these things. It's finding the way through. So when your PhD, you reckon, you got how long left?
Well,
when do you hope to submit?
With the wind in my sails, it'll be January next year. Submit.
Brilliant. Okay, and you're hoping to stay on, going to postdoc and stay in research.
Yeah, it'd be good to see the project right to the end.
Your bit or the low cell?
The low cell project. It'd be good to see that.
Yeah.
Once it's been deployed and get the results back.
It feels like a real worthwhile project to be involved in. Will you get to go out there at all?
Yeah, hopefully for constructing and making sure that everything's up to standards when it's actually deployed.
Yeah.
Hoping to go out, yeah.
No, it's amazing. I mean, I as we mentioned before, I did my PhD. It was kind of interesting, but it didn't feel like it had that immediate impact, whereas what you're doing is going to affect people's lives on the ground in communities that kind of really need it. So it feels like a really rewarding project to be involved in.
I hope so.
So yeah, well, I hope that goes really well. Thank you for coming in and showing this, and obviously hiding the secret bits in the middle there. Wish you well in your PhD, and let us know how it goes. Thank you.
Thanks, Rod.